My name is George Rovithakis, and I have the pleasure and the honor to introduce you our semi-plenary speaker, Professor Song, at the Chongqing University of China, currently director of the university's Artificial Intelligence Research Institute. His research interests are broad and span areas like intelligent systems, guidance, navigation, and control. Also, bio-inspired, adaptive, and cooperative systems with focus on data-driven control and machine learning methodologies. He has published 12 books, over 400 papers, and holds 100 patents. Professor Song is the editor-in-chief of the IEEE Transactions on Neural Networks and Learning Systems. He has also been recognized as one of the world's top 2% scientists by Stanford University. And today he's going to talk about neural network learning-driven automatic control and automatic control for machine learning. So, Professor Song, the floor is yours.
Well, thank you very much for the kind introduction. Good afternoon, everyone. It's my honor to be invited to give the presentation at the ECC. And also, I'm so pleased to be here, see you guys coming. Thank you for coming. Regarding my talk today, I'll be talking about learning for control and control for learning. By that I mean, from left to right-hand side, we'll talk about using different kind of machine learning methodologies, such as neural network, to reconstruct, to approximate some kind of uncertainties. By control guys, we know that the dynamic systems normally involve uncertainties and nonlinearities. So the task of learning is try to reconstruct, try to compensate the uncertainties. Use that as part of information to build the control in a loop, control the system, so that, for example, we can make a robot move from one target to another place. So that's from left to right hand, we say it's a learning for control. But from right hand to the left side, we're talking about control for learning. By that we mean we use a control mechanism, we use feedback to enhance, to improve the learning process in terms of fast convergence and more accurate results, things like that. So today, I will be talking about both, but my main focus will be the first one. If we have time, we'll talk about it later a little bit more. Okay? Well, here it involves, we're talking about neural network, we'll talk about learning, we'll talk about control. So maybe it's a good time for me to pause for 1 or 2 minutes to mention about this journal here, as George mentioned. I assumed the position as associate editor-in-chief for this journal about 2.5 years ago. And doesn't work. Let me just stand here. This journal actually is keep growing in terms of the submissions. As you can see here, the submissions grow exponentially from 3,000 about 3 years ago to almost 7,000 submissions. And currently, the acceptance rate is somewhere around 10%. As compared to the previous, like 28%, 18%, 12%, and so on like that. So that means it is getting more and more popular, but also very competitive. We currently have 10 senior editor and more than 200 associated all over the world. Now, for control community, we may wonder, what kind of work could be considered as relevant for this journal. That's something I will talk about here today and from the rest of my talk. Primarily, we need something about control. Of course, we need more relevant contribution in neural network and learning systems as well, okay? So when we talk about learning, neural network, or artificial intelligence, we know that this is some kind of a topic very hard, and AI seems to be everywhere. But if we look at the real situation here, we basically have like, three parts. The very left one is related to the data collection, data management, and the data, maybe some kind of pre-training stuff like that. And in between, that is something which is more important and also equally important, which means we make use of data to do something, so that rely on different kind of algorithm, okay, different kind of neural network, stuff like that. Now, with that algorithm processing the data properly, we come up with a different kind of application that could be, image processing, target detection, and control manipulation. Of course, for most of us, perhaps are interested in or measuring the third part, by making use of data, which could either be the data collected already, or maybe the data we collect or censoring back online. Through the algorithm processing, we want to do the control. We want to do the manipulation, stuff like that, okay? So with that, then for control guys, for neural network research guys, basically we have like two kind of main research directions. The first one is basically focus on the network or neural network structure, property, and those kind of different styles, such as we know that BPNN or recurrent neural network, or Hopfield neural network and stuff like that. So that's for the purely for neural network study, for structuring, for learning, and so on like that. And another major research direction is based on those different kind of neural network. With the information from there, with the property of those neural networks, we build a controller. We build a control strategy for the system, okay? That, of course, come up with many different kind of ways to do so, all right? So that's basically the so-called neural network control-related research major directions, two types. One, structured neural network itself study. Another one is make use of the neural network structure to design control strategy. Now, when we talk about design control strategy, basically it is something like, like this figure showing that you have to train, either online training the network, offline training the network, to make the target, to reach the target, all right? For example, like this one here. Now, here comes the very interesting question, or the fundamental question, what exactly we mean by neural network-driven control. Let's take this system, for example. This is a very simple first differential equation, dynamic equation. You may consider this like, automobile vehicle, the velocity tracking control, or even the tracking error stands for X, and H stands for the uncertainty here, and the U is the driving force. All right? Now, we know that if H is available, this problem is very simple. We just design the control in this way so that we finally end up with a very beautiful closed-loop dynamic equation so that the tracking error, X, could converge to zero exponentially, all right? That's basically everybody know regarding the control design, or we call it model-based design. However, the real challenge comes from this part, in which the control is based on the availability of H. But H, as I mentioned, it stands for the lumped uncertainty and disturbances and nonlinearities of the system, which is normally not available. Therefore, we have to do something different by using the so-called neural network to do reconstruction, to reconfigure to approximate such nonlinear impact, so that the control turns out to be a little different, replace H by U0 and M. Now, this is actually using, as a matter of fact, we are using the neural network concept now. Here, basically, we replace H by neural network so that the neural network here plays the role. In other words, the neural network unit is in the loop. So by that, we mean neural network-driven control. Now, the key we are doing here is we are doing the substitution by using neural network to replace the previous uncertainty. But the real part, the very challenging issue actually comes from here, which tend to be actually the major content of my talk. On one hand, neural network-based control or using neural network concept to design control, we are using a so-called universal approximation theory, which play a major role to deal with uncertainty. But on the other hand, this substitution, this kind of reconstruction, or universal, or which we call universal approximation theory, has the preconditions. If we look at the previous literature, we know that this kind of universal approximation theory has 3 fundamental conditions that has to be taken care of. So the question here is, what if 1 or 2 or any of the condition is violated? Then what will happen to the neural network-based control? This really involves the reliability, functionality, and the effectiveness, or even trustworthiness issue. Okay? So we talk about those things here when it is safe to put the neural network in the loop. Okay? And what if any of the conditions is not satisfied? What's going to happen to the corresponding control strategy? And more importantly, in design such kind of control, how can we guarantee, how can we make sure that those conditions are automatically satisfied all the time during the system operation? Because those conditions have to be satisfied simultaneously, okay? Then we'll talk one by one and also give some example how to deal with that, all right? Now, getting back from this figure here, we know that for the simple neural network, even with 2 training or stimulated signal, Z1, Z2, basically it is training that, get weights, and then get output. That output is meant to approximate the uncertainty or unknown signal, okay? So mathematically, we have this one here. On left-hand side is the unknown function or unknown signal. On the right-hand side, we have 2 parts. The first part, everybody knows that is we have like a basic functions, hidden layers, and weights, and also the construction error. A reconstruction error, okay? So mathematically, that's the equation over there. But like I said, we have to pay attention to those 3 conditions. If we re-examine the previous, the literature, the original textbooks or papers which mention about this approximation theory or this equation, we learn that there are at least 3 very fundamental conditions. The first one says that the function to be approximated must be continuous. The immediate question might be, what if the function or the signal is not continuous? Maybe like a discontinuous or jump function. For example, our mobile robot or whatever robotic arm move from one place to another place, hit accidentally with the obstacle. That obstacle will in turn act as a jump disturbance to the system. So that might cause some kind of discontinuity as well. So in that case, the signal overall is not going to be continuous anymore. Now, second condition, that says the training signal for the neural network, or the input signal, sometimes we call stimulated signal, must remain compensated, which means from the beginning to the end, this training signal must stay within certain range. Okay? So how can we guarantee that? That's something we have to guarantee, to make sure it's satisfied. In order for us to use that equation to do the design, to do the analysis. Number 3, this condition is even more controversial because it says that in order for that equation to be true, we must make sure that our constructed neural network must have sufficiently large number of neurons. Now, how large is sufficiently large? That's a question is very hard to answer. That's why I say it's kind of controversial. Okay, but we need those 3 conditions be satisfied simultaneously. So when we do the control design, when we do the experiment analysis, those conditions, unfortunately, are either unconsciously ignored or purposely ignored. By purposely, we mean they might realize that those conditions have to be satisfied, but somehow it's hard to make those conditions to be satisfied. So just simply ignore, just pretend that there's no such condition at all. By unconsciously, I mean some work, theoretical work, even didn't realize that those conditions has to be addressed. Okay, so here we will try to, discuss how those conditions should be addressed and how the corresponding control algorithm should look like. All right. More than that, here we will, in addition to that, we'll do something like those 5 fundamental issues. The first one, of course, is regarding how to deal with the discontinuous situation. The second one is how to guarantee the training signal to be always maintain the so-called complexity. And number 3 is to address how large is sufficiently large for the number of neurons. Okay, here we'll introduce the way we call it a self-growing number of neurons by growing, pruning, adding, and removing this kind of mechanism to indirectly address this issue. Okay? And of course, number 4 is also another issue we need to mention, very interesting, because most of the work, theoretical work, or real application examples, we normally think about the weights to be something unknown but constant, which means physically the weight is time invariant. But the real situation for biological systems to be able to adapt to the environmental stuff like that, the real weights not only unknown, but actually it's also time varying instead of time invariant. Okay, and that will actually, like I will mention later on, will create a problem for most of the existing control methodologies, even for the control itself, also for the analysis, because time varying is different from time invariant. Okay, and number 5, I will also mention something about so-called diversified basic functions. Remember that when we construct neural network, the basic function, we did not pay much attention to that, either a single fixed structure, but we want to look at more than just single. It's going to be diversified, different kind of combination of basic function. That will bring us what kind of benefit by doing like that way. Okay, so those kind of things will be the focus, as I showed in this figure. So let me talk that one by one, okay, briefly. Now, first, about the neuroplasticity. What does it mean? Well, it basically means this. It's actually motivated from the real biological system. Lots of experimentals show that not only the weight is adapting, it's keeping changing, but also the so-called excitability or stimulant function or basic functions are also changing as well. So this motivates us to consider design a neural network in which not only the weights are or should be continuously adjusting, but also the activation function should be self-reconfigured or should be updated as well, okay? If you recall that most of the time, the strategy, whatever, we are just focused on the weights. Never think about the activation function or basic function should be adjusted as well. But the real biological systems properties suggest us both should be simultaneously adjusted. So by doing that, we could increase the learning capability, the memorizing capability as well. So overall, the reasoning and learning capability will be significantly increased, okay? All right, now, regarding the weights, like I mentioned earlier, traditionally, like I said, we treat that as unknown but constant. But the real situation is to get used to the environment. The weights actually itself is also varying, even though maybe the varying speed is not so quick, but it is not constant anyway. So in this case here, that should be taken into consideration when we design the control or neural network-based control, especially for stability analysis. So here is perhaps why we know that most existing work here simply choose or simply assume that the unknown ideal weights is constant. Because when W star, the ideal optimal weights is constant, the derivative turns out to be 0. Therefore, this term is not going to affect the stability. But if it's constant, if it is not constant but time varying, then this is no longer to be 0 derivative. Therefore, that term will be playing its role in the stability of the system, will affect the whole overall performance as well. We have to deal with that. So that's perhaps why most of the time, most of the existing strategy, neural network-based results, simply assume that the unknown weights are constant, because now we make the whole analysis much easier, because that can disappear. But when this term is no longer 0, if it is time varying, you have to deal with it. So in other words, generally speaking, if consider the weights is unknown and time varying, the most existing control strategy has to be at least modified. Otherwise, it's going to be invalid, okay, if this factor is taken into consideration. Fortunately, even though it's time varying, but of course we can assume that such variation rate could be somewhere, it cannot be infinite large, okay? So relatively small change or variation, then that's going to be a reasonable assumption. So based on that, then we can actually do the stability analysis by using, the robust adaptive control method, okay? So using our considered time varying ideal weights will make the analysis closer to the real biological systems. On the other hand, the difficult arising from such non-constant weights, it is not so hard to deal with if we use the currently developed robust adaptive control, okay? So let's then move to the next one, number of neuron. Like I mentioned, that equation, that approximation theory specifically require our constructed neural network to be sufficiently complicated with sufficiently large number of neurons. Therefore, they have such capability to approximate any unknown signal, okay? But how large is sufficiently large? That's really hard to deal with. Because of that, it is very likely that we might end up with two extremes. One is we choose the number of neurons to be too large, okay, unnecessarily large. For example, a 3-joint robot, move a target from one A to B, you might need like a 30 neuron, but since we don't know how large is sufficiently large, we might end up with 3,000 or even 30,000 neurons, right? So unnecessarily large number of neurons could cause unnecessarily heavy computation, resources be wasted. This perhaps explains why the DeepSeek could come up with almost the same result as a ChatGPT with much less computation resources. That is something maybe more or less related to the number of neurons for the specific task, how many neurons would be sufficient, okay? This is one of the extreme, but another extreme situation might be, since we don't know how large is good enough, we may end up with too little, okay? The number of neurons is too small, okay? We need, for example, 300, then 300, you end up with like 40, 30. That's much less than the required number of neurons. Therefore, the corresponding neurological unit will lose its capability for reasoning, for learning, for approximation. So either way, it's going to be a trouble. So that's why we keep saying that this relates to the functionality, the trustworthiness, and also the efficiency of the neural network. So how can we come up with a figure, number of neurons, which is not the perfect number, but very close to what we need? Frankly, there's no solution for this. But one way we tried is to introduce the so-called self-growing number of neurons. By that we mean initially we guess the number, use experience, and then make the number of neurons not fixed but growing, but increasing. During the system operation, we could add some certain number of neurons, and the adding mechanism or criterion would be another story, okay? Could be like a performance-related, stuff like that. Then keep doing like that. A certain period of time, if the system performance keep improving, keep stable, we can gradually remove some, okay? Therefore, by doing this, we basically involve the number of neurons to be growing, to be removing or pruning. Finally, we can end up with a figure, number of neurons, which is just perfect for this particular application. So that's one way we attempted. Turns out to be pretty effective, okay? And of course, for example, the could be very simple using the some kind of perspectives, strategies, and to adding, to pruning, as long as some certain kind of condition is satisfied. So this is something different people could come up with different kind of solution, but the concept is the same, okay? Indirectly addresses that condition, all right? Okay, now, keep going. Talk about the activation function. Now this one here, like I said, still we get the inspiration from the real biological system literature and experiment. We see lots of literature in cell science and literature, cell science, lots of research, especially experimental research with that, indicating that the stimulating human brains into stimulating action for different area, for different kind of incidents, the reaction is different, which suggests that we will have to consider more than single fixed stim activation function that is against the real biological system property. We should consider diversified, more than one, but a very variable, diversified stimulation function, which allow the whole system to carry much richer, more complex information in the network, okay? That way, it is closer to the real biological system property. So in other words, instead of use what we have like a sigma function, hyperbolic function, that's it, fix it like that, we can use at least a combination of them, okay? Later on, we'll see not only compilation, we can actually introduce a way to make the stimulation function to be reconfigured by itself. Not only one, not just simply 2 or 3 simply combined. We can make it a change during the system operation. That way, logically, it reflects, the real biologic system's stimulated function, which is not fixed, which always change, different reaction, different kind of stimulation, and so on like that. Okay? So that's something about the diversified activation function. All right, now let's keep going. Another one, like I mentioned earlier. The training singular, the stimulated singular for the neural level must be kept within certain range from the beginning to the end of the operation, also called input complexity issue. How can we guarantee this? Well, this is actually a long story. This phenomena has been noticed a long time ago. As early as 1992, a group of researchers from MIT, they are doing robot experiment. They find out that sometimes the using neural network even does not work well. I mean, even worse. If they switch off the neural network, it works even better. All right, they proposed a way as like a space partition, which means during the whole operation of the system, they divide the whole working space into 2 parts. One part is for the neural network works well. The rest of the part means the neural network does not work well. So when we do the analysis experiment, we try to switch off the neural network. If it is operating within the range that neural network is not reliable, and then switch it on when it is reliable. That's the original idea proposed by this group. But as you can see here, this method sounds very interesting, but it's not practical because the overall operation space, we know that for sure. But to divide into 2 parts, one of the parts NN works well, one of the parts NN does not work well. It's very hard to determine. Okay? You really don't know within which area the neural network works good, in which area the neural network does not work well. So it's not practical. And later on, we had a paper in robotic system. We call it the fail-safe method. Basically, our strategy is based on the recognition that the neural network during the whole system operation might not be so reliable, might fail a certain kind of range. Then take that consideration, we design the control. So by that we mean fail-safe. But still, the overall system is really related to the approximation theory. Either one or more of the conditions are not satisfied. Okay? That's why the neural network does not work well sometimes. That's real reason. Okay? Anyway, now keep mentioning later on, a group of researchers from University of California, Riverside, they come up with a solution. Okay, still, they realize that the training signal must be within capacity. Then their solution is to use a so-called supervisory method. Basically, it's similar about monitoring the operation of the neural network unit. Whenever the neural network, whenever this overall training signal enter into certain range, then they switch in the neural network. Before that, they do not use the neural network unit. So that's the ideal. Switch in. But still, that's something you have to switch stuff like that. Later on, we noticed that a group of researchers from Singapore National University, they published some work regarding control dynamic system under constraint, like output constraint, state constraint, that kind of work. then we realized that that type of technology, so-called the baronial function, could be borrowed to address the so-called constraint of training signal to stay within certain range, okay? So that's basically is based on this so-called baronial function here. As you can see, mathematically, it looks like that way. Now the denominator, I mean, beta represents a certain number, and S stands for the training signal. Here we're talking about a scalar signal. If it's more than one vector training signal, we just use a normal, okay? Now you can see here the denominator could be 0 if S equal to beta. At that time, the denominator is infinity, and the overall value is infinity. Therefore, even though we take a log, still infinity. So draw the figure like this. It's corresponding to the dashed line here. So negative beta 1, positive beta 1 will give us infinity large of the function. But other than that, somewhere between, the function will always be bounded, okay? And interestingly, this function is 1-by-1 mapping. So we have, if S is within the beta range, the function VB is bounded. Reversely, if the function VB is bounded, for sure, S is going to be less than beta. That's 1-to-1 mapping. So that means if we could design the control so that we can make the function, the upper function to be bounded, then we can guarantee the signal S will be within the beta. But as you can see here, this is a very important precondition. That is, initially, the denominator will not be 0, okay? If initially it stays somewhere that violates the condition, then the rest of the story ends. So we need to make sure that this compact set must be satisfied from the beginning to the end, which means including the initial time. But now here, mathematically, we know that we have to assume that initially it is satisfied. But the actual situation might be initially it does not satisfied. So we have to address the initial condition issue. Fortunately, we have a work called the deferred time-varying constraint. We basically try to use that to convert any non-zero initial condition, transfer that to the 0. Therefore, 0 is always less than beta, which means no matter what initial conditions, by using this transformation method, we can for sure guarantee that initially it is satisfied as well, okay? By doing that, then we solve this so-called compact set issue. Even the initial condition has to be satisfied as well, okay? So that's those kind of fundamental issues we have to take into consideration. I have to pay attention to when we construct the neural network, when we use that to design the control, okay? If the those issues, either one of them is ignored, it is basically some kind of flaw, okay? We have to address that. So with those things considered altogether, then we are interested to look at what the neural network should look like, okay? Now, here, of course, first of all, mathematically, it should look like this one here. Left side is the neural network output. Now, the first sigma stands for the diversify of stimulated function, because L could be 2 or 3 or 4, okay? Traditionally, it's 1. Now, the second sigma, M, K, T, I specifically put the preferences T to emphasize that the number of neural is not fixed. It's changing with time. It's growing, okay? As a matter of fact, inside there, not only the weights is treated as unknown and time variant, but also we have A and the P, which stands for the adding and the pruning process into the functionality, okay? And of course, Z belongs to B, stands for always guarantee. It is inside the compact set, okay? So that's a mathematical equation, the approximation theory looks like. And the structure one of the structure turns out to be like this right here. At first glance, you might think it doesn't look much difference. But if we look carefully here, vertically, basically that stands for different kind of basic function or stimulation function. Here, the top one might be is tangent function, the second one might be hyperbolic, and so on like that. So we have this network reflect the fact that it involves diversified stimulation function. Now, horizontally, we look at, for example, the middle one. Different colors stands for different kind of neural adding and prodding. So it's going to be expand or reduce based on if there is a neural network, neural removing or adding action is involved. Okay. So overall here, that actually reflects or takes care of what we just mentioned earlier. Has to be diversified, has to have a mechanism for number of neural growing, pruning, mechanism involved as well. So in some sense, it has capability for deep learning and broad learning as well, okay? And as for how to prodding, adding neural, like I mentioned, it's quite, it's not that complicated. You can come up with different kind of strategies to do so. And there's one thing we have to be careful here when we talk about the adding. This is some of the formula. For example, we use that to design the control. I mean, to use a particular example to show how to design this strategy. The dynamic equation here is a so-called normal form nonlinear system with plus minus disturbances, which means that could be discontinued, okay? Then the rest of this is standard. But look at the control here itself. The neural network control unit, the denominator has beta squared minus S squared. That is to take care of the so-called composite guarantee, okay? On the top here, 2 sigma, of course, stands for diversified stimulation function, and also time-varying neural, adding, prodding, etc., all are reflected in this analytical expression, okay? And of course, the detailed analysis can be shown here. Well, sigma is not showing there. Anyway, the detail is to show how can we do the approximation to the analysis and deal with the time varying unknown and time varying ideal weights, stuff like that. And it's a controller, and this is the structure. Here is number of growing, neural number growing. And one thing, of course, as a design technique, you have to make sure that the adding process has to be smooth. You cannot all of a sudden add a number of neural to the system and a number of all of a sudden remove a number of neural. You have to make the whole process to be smooth. So that's very easy to do so by introducing a smooth function. By doing that, the whole action remains continuous and smooth. And doing this guarantees stability, or we call explainable, is guaranteed by the rest of stability analysis, which of course it's not a good idea to talk about in more detail here, right? So to summarize, basically, for this type of system, the neural network-based control looks a little different from traditional one, because in which the diversified stimulation function, number of neural growing, and the complexity, etc., are all taken into consideration in the strategy. And we did some kind of simulation very quickly. For example, this one, 3-joint robot, do the experiment here. As you can see, the mathematical equation is quite complicated. If we use model-based, that's going to be a headache. But use the one we just showed that, especially, we are interested in looking at, for this particular application, how many number of neural you used. Now you can see here, initially we guess a number, and increase and reduce, and very quickly we end up with something like that. The number of neurons is not that much, okay, not that big. And basically we are talking about use a robot to draw a circle, okay? Now the enlarged portion is showing that compared to the other one, the proposed method could come up with a very accurate tracking, even though we enlarge the detail, okay? This is for the actuator to be held. Even we consider the fault situation in which one of the motor has some kind of driving efficiency issue. Now again, traditional way is unable to come up with the plot which looks like a circle anymore. But for the proposed method, when we enlarge the arrow, you can see still keep close tracking. The accuracy and reliability is guaranteed by doing so, okay? And again, the corresponding number of neurons for the situation we have actuation fault still could fix, I mean, less than 30 number of neurons would be sufficient for this type of application. All right, now, we actually did an experiment as well by using this so-called use a robot to write Chinese character. You know that in some cases, Chinese character is just like a draw a photo, or just draw a picture or trace the line. So this is basically involved like a tracking. If the tracking arrow is small, which means the data right out turns out to be pretty, otherwise it should look ugly. But for this particular model, if we go through the traditional way, establish the mathematical equation, even though it's just rejoined, it turns out to be very complicated. And fortunately, we don't need that. And we use the method we introduced today. Doing this kind of experiment, it turns out to be, let's see if I can. Yeah, writing like a Chinese character stands for the computational intelligence. It basically traces the trajectory and come up with accurate, relatively high accuracy tracking so that the overall Chinese letter or character turns out to be, if you happen to know Chinese word, looks actually as acceptable, okay? And also we have applied this to the human walking robot. Very quickly, the stable walking, balance, and rejected disturbance is very important. Now for this one here, basically we can use this type of neural network control, make it work quite satisfactorily. Okay, now, here will be something regarding, come back to my title, Control for Learning, and also some kind of possible extension as the time is approaching. Very quickly, for control for learning means we use control feedback, control mechanism to improve the learning process so that the learning process will converge quicker, smoother, with higher accuracy. For doing that, basically we consider the learning process to be continuous dynamic equation or dynamic model or dynamic systems. Therefore, we can use our control to speed it up. The detail here is shown in these slides, but I don't have much time to go into the detail because right now here, let's consider further development here. For example, use PID. Similarly, that could speed up the so-called learning process. All right, this is one of the possible extensions to do. Okay, another one, again, go back to what I said for the weights, for activation function, for learning mechanism, and the training method. Traditionally, we have to pay attention that in general, the weights is keep constant. After you're training that, it keep constant. That's what we did. And for the activation function, it's a fixed structure. It's either sigma or time like that. basically this type of activation function means that whenever it's larger than a certain value, it's treated as 1 or negative 1, things like that, which means they are doing something like a head-tail clipping. So that is inevitably lose quite a lot of rich context. If it's bigger than that, we better reflect that fact. But for this type of basic function, that is impossible, okay? So what should we do? I mean, what's the possible extension? Well, we should keep, like I said, the weights time variant online adjustment, and also for diversified basic function, even self-adjusting basic function, which beyond to linear, to constraint bounded to conditionally bounded, linear growing, stuff like that. Therefore, you might be able to deal with much more difficult situation. And as for the adjustment mechanism, we should use so-called dual adjustment, means both weights and the activation function should be adjusted simultaneously, okay? For example, this is a well-known PID control. If we look at it from neural level perspective, it's really a very special neural level because they have constant weights with that type of basic functions. Now, on one hand, PID control is very popular, it's very useful. But on the other hand, if the system turns out to be more complicated with determinism, then PID with constant gain is not working very well, okay? So that reminds us, what if we, okay, corresponding to this neural level, I mean, for constant PID looks like neural level. But on the other hand, if we look at the real situation here regarding the activation function, instead of using the sigma or time, those kind of bounded function, what if we consider the one on the right-hand side, which actually I show you here, it's like a nonlinear tree function. That's going to make much difference. For example, here, if this is the red line is actually the nonlinear function singular here, but if we use a traditional bounded basic function, no matter what, we can only get the bounded singular. Other than that, it cannot be reconstructed anymore because mathematically here, this is unconditionally bounded because W is bounded, phi basic function is bounded, and delta is reconstruction error has to be bounded, otherwise it doesn't make any sense. So the right-hand side is unconditionally bounded. But what if the left side, the signal, is conditionally, not unconditionally bounded? Which means in that case, by using this kind of idea, we will never ever be able to deal with such situation, okay? So that reminds us, consider the nonlinear conditionally growing basic function. As you can see here, they have a different kind of way to approximate the singular. Sometimes linear, sometimes nonlinear, and stuff like that. That way, if we go back to look at this here, we are able to deal with any unbounded singular approximation, which means if the operation condition enlarge it, this kind of network might work as well, okay? Now, getting back to that reminds us to use a new neural-driven PID, which means, as you can see here, looks similar, but there's fundamental difference. The weight is not time varying, I mean, it's not constant anymore, and the basic function inside the PID, proportional integral, and derivative is not a simple function anymore. It's also nonlinear basic function, changing with proportional, changing with derivative, changing with integration, okay? Now, talk about integration here, of course, is even more interesting because whenever we do integration, we will always have to address the so-called integral saturation. But if we use a nonlinear basic function there, we can build the bounded or even self-disappearing integration function. Therefore, it literally has the capability of wind-up phenomenon, okay? So by doing that, then by doing that, we could come up with this type of networking in which time-varying weights, diversified stimulation function, self-configuring basic function here, and more importantly, the overall system is explainable because it is based on the proof stability theory. And finally, the network looks like this way. Now be careful here, the weights only require the proportional integral and derivative. However, the time-varying weights, we have to use both of them, which means we are using the current information, we are using the experience, we are using the predicted information altogether to update the weights. Therefore, the corresponding control turns out to be highly nonlinear, neural-driven PID control strategy. Okay? Well, all those kind of talk, those information can be found out from those publications in TNLS, TIE, Automatica TSC, and SMC. If you are interested in that, you can, get those papers and examine that in more detail. Due to time constraint, I have to stop here. Thank you very much.